Okay, so now that we checked the velocities, let's try to optimize these pipes. So to do that, we have our pipe optimization function on the Hydra panel. It's called pipe optimization or initial pipe selection. So you can optimize the existing pipes that you defined by yourself, or you don't have to have pipes selected at all. You can just run it for the first time and get the optimal solution. We will optimize the existing pipes. So here, first of all, you can create some, again, configurations, or it's better to say maybe zones or groups, because if you just, I don't know, here you can select the total cut, the whole catalog. You here can define the target velocity, and if you click start, of course, you will get results. The results will be pretty good, much better than what would you define manually. But if you want to decrease the time necessary for the software to compute, and if you want to increase if you want to increase the quality of the results, if you want to get as great results as possible, then it is recommended to create some groups. Now I will show you why. For example, let's create one group, and I will call it transport pipeline. Okay, here you have your selection options. So you have to define which parts of the system will be assigned to that group. Let's go by arrays and let's select this array. Okay, so here we have this part of the network under this group. Let's create another group, and here I will call it a distribution network. Okay, let's now select these parts of the network here. You can also use CAD selection to select it more easier. Okay, and now you see that in the default configuration we have 0. So basically we define 2 new groups. And now for each group, you can define what is the target velocity. So basically how this calculation works, you define a target velocity, and the software is using genetic algorithms to find the diameters, to find the pipe diameters, so that the real ending velocity in those diameters, in those pipes, is as close as possible to your defined target velocity. And now for the entire group, you can define single target velocities. For example, let's say for this group it will be 0.9, and for this group, because this is the distribution part of the network, we will have smaller velocities. Let's say the target velocity will be 0.6. This is one way. Or you can use this diameter dependent, which is the option that I like to use, because now for each range of diameters, you can define the target velocity. So now the calculation will be a little bit more complex, because for each calculated diameter, the software will check its target velocity. So for example, if the pipe is between 0 and 100, of course, you can change and define these ranges. Then target velocity will be this, target velocity will be this, target velocity will be this. So this is the option that we will use. So for this group, diameter dependent, and also for this group, diameter dependent. Also, for each group, you can define which pipes can be used from the pipe catalog. This is what I said before. You can, nothing is stopping you, to select the entire group. So we will use this PhD pipes. You can select the entire group. But then in this group, I have the pipes from 32 millimeters all up to 1000 millimeters. And of course, I know that here, for sure, I will not have pipes, let's say, smaller than 200, for sure. And they will for sure not be bigger than 400. I don't know which pipes are optimal here, but based on some logical thinking, by doing this selection, I reduced the time for the software to to compute, and immediately in the start I removed some solutions that are basically not solutions because they are really bad solutions. For example, if you take pipe of 32 millimeters, the software will try to see where this pipe can go, and it will just take time to compute something that is not useful. So this is something that is recommended. It's not mandatory, but it's recommended. And also now for this group here, I will do the same, but here I will select smaller pipes. Again, I don't know which pipes are necessary, but let's go, for example, from minimum 1.10 to, again, I will select 200. Okay. And also here you have some advanced options. You don't have to change the defaults. I like to change some stuff here. So basically how this works, like I said, it uses genetic algorithms, so mathematical method. So here you can define some parameters. For example, the initial population size, I like to increase this to 500. It will not take that much time, but it can increase the quality of the final solution. Also, if the velocities are too high in the network, the software will treat those solutions as bad. So here you can define overspeed penalizations. And I don't like my velocities to be over the target velocities that I define. So I like to increase this overspeed penalization, let's say to 1. And also underspeed penalization. Okay, if you, I prefer to have a little bit larger pipes than a little bit smaller pipes, but because if you have a little bit smaller pipes, then the velocities will automatically be higher. So also I like to decrease this to, let's say, negative -1. Okay, here are also some advanced options that can be changed or not. For example, number of generations, let's increase it to 500, mutation size and number of crossover points. So these are just some mathematical parameters. But of course, if you increase these values, you will get more, let's say, quality solutions. Let's click save, and now let's click start. And now you will see how the software is searching for optimal solution, because that number that we set, initial number of generations, 500. So the software randomly put 500 possible combinations of these diameters and send it to EPANET. And then EPANET calculated, results are back in Urbano, and now we are checking, okay, this result is better, this result is worse. And in 30 generations, the software calculated this, and we see that the fitness factor is 0.16, which is great. I know, but just by checking this number, this is great. So let's check it. For example, let's select this array here. And again, it is not saved automatically. You can check the results. So these were the old results, the low, the small diameters that we had before, and now this is the results given by the software. And again, you see the resulting flows, velocities. These were the target velocities, and this is the difference between the real velocity and target velocity. Let's save these results. Okay, and let's now check this. The target velocities were around 1 for these diameters, around 0.80 for these diameters here. And now the difference between the real velocity, ending velocity, and the target velocity basically defines this fitness factor. So of course it is impossible that your target velocities and real velocities are completely equal, then this fitness factor would be 0, but that's really impossible. So we can check the other results as well. I think this is really good solution, and basically that's it. If you're not satisfied with something, you can continue editing and increasing or decreasing pipes, but I think that this solution is really great. Okay, let's close this, and let's now check our results. So you can see that the piezometric lines changed a little bit. We have here now much more smoother transition, which means that we have smaller head losses. So the piezometric lines look really, really good. Let's now check our data tables again. Let's check it for section hydraulics. Let's select the entire system. And let's sort it by velocities. And now you can see that we have a lot less these red numbers, only 4. And this is the ending parts of this branch network, these dead ends. So this is something that should be expected. But I intentionally didn't go with the diameter smaller than this, because later on we will also include some firefighting demand as well. And if we check the highest velocities now in the network, it's 0.99. So now we have the higher velocities in these parts of the network, and they are smaller than 1, which I think is great for this network. Let's also use T-maps now to check the results. Again, let's apply one T-map for the velocities. Let's show it, and let's place it here. And now you see we have much more green color and much less of orange and red colors. So I think that now the velocities and diameters in our network is really, really great. Okay, so we sized our network. Let's also now check the pressures inside of this network. Let's delete this T-map for the sections. Let's again open our data tables, and let's check for the node hydraulics. Again, we can check these red values. If we go to our data table for the nodes, node hydraulics, let's edit this, and you see here, calculated, no, not this, but this, starting pressure and ending pressure. You see that we have the minimum and maximum values for the pressures for this validation defined as 25 and 70 for the minimum and maximum pressures in the meters of the water level. So 2.5 and 7 bars. Let's check it here. So we see that the smallest pressures are basically in this part of the network here, which is basically outside of the populated area. This is, as you can see here, this marking options. So this is close to the water tank. So this is not a problem. But let's check the highest pressures. And we can see that the highest pressures higher than 70, are located in the bottom part of this network. But of course, that was expected, because we can see the terrain difference in this terrain here is pretty high. So of course that we will have a lot of pressures here. Again, let's use T-mappings to check these pressures in the network. So I will apply one T-map for the pressures. Let's select the entire system. Let's set the legend position, and let's put it here. And now again, you can see these color ranges that I defined inside. You can open it, you can edit it. These are the defaults, so I didn't change anything. So by default, you have these colors going from colder colors to warmer colors. So it goes from 0 to 100, but of course you can add additional pressures as well. So this is the legend. And now we can see where we have these really small pressures and really high pressures. Another great function to analyze this is drawing of the contours. So you can draw these contours by using, again, this predefined configurations, or you can create your own. Let's check, for example, this gradient. This is really nice because you don't define the ranges for the colors. You just choose this color stylist gradient, and it will automatically go from the red values for smaller values to blue values for higher values. So let's just draw it. And now you can see we have color gradient from colder colors to warmer colors. But now you can see that these ranges are not matching completely. They are matching, but they are not matching completely this legend here. So if you want these contours to match your configuration, you have to use the custom color ranges, so custom color ranges, and you can set up, just like for the theme maps, you can set up the same color ranges and define the same colors as for the theme maps, and that is the default. So let's close this. Let's first delete the old ones, and let's apply this pressure custom. Let's draw it, and here it is. Now you see that we don't have the gradient anymore. We have the strict transitions from blue to cyan to green to orange to red. And also it is important to say that these are basically like terrain contours. These are 3D polylines. And if you switch to 3D view, you can also check it in 3D as well. This is basically like a DTM, but not with terrain elevations, but for the pressure elevations. But basically inside of it, you can also choose different data. It doesn't have to be pressure. It can be head elevation, it can be terrain elevation, it can be invert elevation, and so on. Okay. So now we basically come to a conclusion that here would be a good place to place one pressure reducing valve. So let's delete the theme map. Let's remove the pressure contours, and let's now set one pressure reducing valve to this node here. So to do that, let's go to Hydra panel. Let's go to hydraulic node equipment, and here let's set a valve to this node here. Like I said, you have all the EPANET available valves. So you can use, for this case, you can use pressure reducing valve or pressure breaker valve. And I like to use pressure reducing valve. So for the reduced pressure setting, I will go to, let's say, 35 meter of the water level, so 3.5 bars. Let's click apply. You see how the graphics automatically changing. You can also click here on redraw or reindex for the style to update as well. And now you can see that this will go up to the edges of this valve. And also if we go to our profiles, you will see that some graphics will also show here. So you see this is a custom block for pressure reducing valve. Also here we see that the profile for some reason didn't update correctly, because you can see we increased the pipe diameter and the trench remained here. But this is not an error. This is just the profile, the trench didn't automatically update. So again, if you see something like this, just click on redraw profiles, and in a second you will have this. So if we check the results now that we applied a valve, again, nothing changed because we have to rerun the calculation. So let's open hydraulic calculation again. Let's click calculate. Let's save the results. And now you can see that the pressure dropped from 67 to exactly 35 meters. So now if we check our profiles, you can see this pressure drop happening because of this pressure reducing valve. Okay, so now we resolved the pressures. We can also reapply the theme map. So to check it once more, let's go to pressures. Let's show this theme map and place it here. And let's also repeat our contours for the custom pressures. Let's draw it. And now you can see how these colors look much better. So we do not have the red values. We have only the green, cyan values, and also some of the orange values here around our pressure reducing valve. If we open our data tables and now go for node hydraulics, let's check it. Let's select the whole network. And now you see that the highest pressure in the network is 67 meters, which is here just before this pressure reducing valve. Okay, let's delete the theme map. Let's delete also this drawing contours. Okay, and basically now we have our final results here, so we can also check it. And one really nice way how you can check it, I didn't show this, but marking plan, we use it all the time. But here you also have zoom in plan, which is really nice. So you can select, for example, I will select this array here. Let's use zoom to plan. You also have zoom to profile. Let's zoom to plan. And now you have marking plan, but we are under nodes. Let's switch to section hydraulics. And now you can see that for each section, you have values written in the labels. And also you can simultaneously check them in the data table as well. And you can see standard data for the sections like diameters, flows, and velocities. But also you can see for each section starting and ending pressures as well. We can also add the piezometric line or head elevations to labels also. But by default, it is not, because the pressure is maybe enough to check this here.